Hello, everybody, and welcome back to CSE 1322. This is module number 3, section number 5, or part 5, and this is going to be the wrap-up video for module number 3. In module number 3, we've actually covered a huge amount of information. We've started off and we were talking about inheritance. Inheritance was the idea that you may have a parent who gives you some capability. You inherit from that parent a whole bunch of functionality. Anything that is a method in the parent that's public or protected, or anything that's an attribute in the parent that's public or protected, inherently the children get that. And by default, without doing anything, a child of an object is able to then start calling those methods and pretending as if they are themselves. So if we have a mammal and we have a cat and a dog and a cow, and the mammal knows how to implement talk, then all of them will know how to implement talk because of what the mammal gave them. All right. So once we talked about inheritance, the next thing we talked about was overriding methods. So sometimes when you get something from the parent, you don't like the way that they do it, or you need to do it differently. There's a default behavior, which is what the parent knows how to do, but maybe you need to implement a different version of that because that's what suits you. Turns out, as far as talking is concerned, while the mammal may say, oh, the cows will need to say moo, and the cats will need to say meow, and the dogs will need to say woof. And so you're going to need to re-implement each of those in the children by overriding them. And so that's what an override method or an overridden method is all about. The next section we talked about were abstract classes, where we mentioned the fact that sometimes the classes don't really make sense in the real world. It's more of an abstract idea where you want to put down a bunch of detail and you want to have a bunch of methods and maybe a bunch of attributes that everyone's going to share, but you don't actually want to have to be able to create that thing in the real world. And so in the case of mammal's a great example because you'd never really instantiate a mammal. If you walk down the street and you see, oh, look, it's a mammal, you're going to be very confused. You either saw a cat or a dog or a cow or one of the other mammals, but you certainly didn't see mammal. That doesn't make sense. Ooh, look, it's live. So you're going to want to make sure that abstract classes, that they make sense to you. You would use abstract classes when it's more of an idea rather than it being a concrete thing that you need. And when it has abstract methods in it, it has to be an abstract class. Abstract methods just mean, I'm not going to write the detail, I just need you to know that there is such a thing as the ability to talk or the ability to walk or whatever it is. All right, the next thing we talked about were interfaces. And interfaces, we said, are just like abstract classes, except absolutely everything in the interface is listed as abstract. And so an interface is just the extreme of a scale where you had concrete classes and then abstract classes. Interfaces are just the extreme of that. In the real world, interfaces are probably used more than abstract classes because realistically, if you need to have abstract methods, you might as well just have all abstract methods and use an interface. But they certainly both exist, but you'll see interfaces more. Next up, we talked about polymorphism. Polymorphism is a weird thing to explain, but the very basic explanation is if you have a parent and you have a child, polymorphism allows the child to change from being its child to being its parent or its grandparent or its great-grandparent. And when I say change, really what that means is it can actually just be instantiated as the child on top of a variable that is of its own type or is of its parent's type or grandparent or great-grandparent or even any interface that it is implementing. All of those are usable as the type on which the variable can be created. And then finally, we've used array lists in here, and we're just going to see an example where we use some array lists to help understand all of this. So let's start off with a class mammal because it's a good example. You might wonder, why do we keep talking about mammal? That doesn't make sense. Why would I ever make code for mammals? Well, it's just a really good example that everybody can understand from the real world. And in general, object-oriented programming is supposed to be modeling the real world. So mammals just tend to be a good example. But yeah, you're right. You'd probably never be writing mammal code. So class mammal has, in this case, some attributes, which are all going to be private. And then it has a public method called breathe, which allows it to breathe. All right, it has two children in this example. We have a class dog and a class cat. And both of those are going to inherit from mammal. The dog is also going to implement an interface called talkable, which requires it to have a method called talk. So if we look at our class dog, it must have a talk method because of the interface out to the right. This talk method that we're getting here is coming from here. And then it also has to inherit the breathe method from above, so it naturally knows how to do that. We're not overriding the breathe method here because we're happy with what we got from the parent. When we look at the class for the cat, on the other hand, we see that that class did override breathe because it's not happy with the way that it works. And then finally, we can see that the dog is also doing some doggy stuff. So let's take a look at that in code. So there it is on the slide. I'm just going to pop over to IntelliJ, and I've already written all of this out. So I'm just going to run through these. This is the same as the UML diagram that we just looked at. I just coded it for you. So we have public class mammal. It has one method called breathe, and that method has just printing out generic breathing. So mammal, in this particular example, is a concrete class. Now, that's not how it's supposed to be. It's supposed to be abstract. I forgot to put that word in there. And so I'm going to come up here and say abstract class mammal. All right, so great. That's the implementation of this first thing, which is the class mammal. All right, and it has its breathe. Next up, I'm going to implement the talkable interface, public interface talkable, and it has void talk. And that's this down here. That's our public interface for talk. Next up, we have our dog. And what the dog is going to do is it's going to implement talkable, and it's going to extend mammal. So it extends mammal, implements talkable. In order to do that, it has to have a talk method, and that's because it got that from the interface. It also has to have a breathe method, which it inherited, but we don't have to do anything for that because that's inherent. And then it turns out our dog also knows how to do dog stuff, which just is that they print out wolf. And then finally, over in our cat class, again, it extends mammal because it's a child of mammal. And in this case, we're overriding the breathe that we got from above to print out I have kitten breath. Okay, so based on all of this, the next couple of things that we're going to do is we're going to talk about what is possible given this set of classes inside of my main method. If I can get this to erase, which apparently I cannot. Okay, we will not be erasing that slide. Great. So if I go over to my main method and I clear out all of the junk that IntelliJ puts in there for me, here's the question. Which of these things am I allowed to do? So the first one is I'm going to say mammal m equals new mammal. Is this allowed? So you'll notice that straight away it underlined new mammal. And very specifically, it underlined new mammal because that's where the error happened. It's perfectly fine for me to have a mammal m variable. That's okay because I have a mammal class, but I'm not allowed to do a new mammal because mammal is declared abstract. So had I not forgotten this abstract word, or had I forgotten the abstract word like I did a minute ago, this would be a perfectly fine statement. But as it's written right now, because mammal is abstract, I'm not allowed to do this. And indeed, it says mammal is abstract and cannot be instantiated. Okay, so now let's talk through all the children. So cat C is equal to new cat. Is that allowed? Well, the answer is yes. It's allowed because cat is a concrete class. It inherited breathing and it chose to overwrite it. It's not implementing talkable, so it doesn't have to have a talk method. So it has met its contract. It has done everything it's supposed to do to be a concrete class, and as such, I'm allowed to instantiate it. So yes, cat C equals new class. Our new cat is perfectly valid. They called it C1. All right, next up we have dog D1 is equal to new dog. Is that allowed? And the answer there again is yes. The dog extends mammal, so it inherited breathing, and it implements talkable, which required it to write a talk method that it did. It also wrote another extra method, which we'll talk about that in a few moments. But yes, all of that is perfectly valid. Dog D1 is a perfectly valid dog. All right, next up, dog D2 equals new cat. So is this allowed? Well, you might think this is polymorphism. I've got a dog, I've got a cat, and I'm trying to put the cat on a dog variable. And that seems to make no sense in the real world, but maybe it makes sense in code. Let's go back to our little slide over here, and let's see if we can erase it. Now we can. Can we put a cat onto a dog? And the answer to that question is no, we cannot. These are not children of each other, they're siblings. So the rule with polymorphism is you are allowed to use anything above you, but you're not allowed to use anything next to you. So I can make a mammal and put a dog on it, that's allowed. I can make a mammal and put a cat on it, that's allowed. But I cannot make a dog and put a cat on it because they are not parent-child, they are siblings. So no, this is not allowed because siblings. I never thought I'd write, but here we are. All right, so the next thing we're going to look at is cat C2 equals new dog. I think this one's pretty obvious. If it doesn't work for the dog onto the cat, then why would it work for the cat on the dog, or vice versa? So no, not allowed because siblings. Same exact problem as the one above it. All right, next up we have talkable T1 equals new dog. Okay, this one's a bit goofy. The thing on the left is an interface, talkable. If we go back to our talkable interface, we see it has to have a talk method. And then onto it, we put a new dog. Well, the dog implements talkable, so it is effectively a child of talkable. Now, it's not really a child because interfaces are not parents, but effectively it's a child of talkable. So I know this is confusing because I said this is not allowed, but now I'm telling you this is allowed. And in the diagram, they kind of look like they're the same thing. But really, talkable is something that you're implementing here. So effectively, this is more like it's a parent. So it probably should be more up here than next to it on the side, just a matter of how you drew it. But either way, yes, it is allowed for you to say talkable T1 equals new dog. Because the dog implements talkable, you are allowed to do that. The next example is talkable, oops, something stupid. The next example is talkable T2 equals new cat. Now, is that allowed? Well, the answer to that one is no. And you again see it underlines it. You cannot do that. Why can't you do that? Because the cat is not a child of talkable. It doesn't implement talkable, so therefore it's not allowed. I can only do it on the dog because the dog implemented talkable. So talkable T2 equals new cat is not allowed because cat doesn't implement E-M-E-N-T. That still is missing another E. We'll get there eventually. Okay, all right, so next up, we have mammal M1 equals new mammal. We already tried that. That is not allowed, and it's not allowed because mammal is not, or sorry, is abstract. Since mammal is declared abstract, I cannot instantiate it. All right, so let's look at the next one. Mammal M2 is equal to new dog. That's what it says next. Yes, that is allowed. This is an example of polymorphism. So the dog is a child of mammal. And if we go back to our diagram, we can see that the dog is a child of mammal. That's this relationship right here. As a result, polymorphism states I can make a variable of the parent, and onto it I can place the child. So I'm absolutely allowed to say mammal M2 equals new dog. The parent is the thing on the left, the child is the thing on the right, that's allowed. And likewise, mammal M3 is equal to new cat is also allowed for the exact same reason. A cat is a child of mammal, so therefore it's allowed. All right. Next up, we have cat C3 equals new mammal. Okay, this is not allowed because the directionality is wrong. So it is the case that cat is a child of mammal, but it's not in the direction that we need it to be. I cannot use the child as the type and then try to put the parent onto the child. That's not allowed. You're allowed to put the child on the parent, but not the parent on the child. Also a weird sentence. But the important part is that in order for anything to work, the thing on the left must be equal to or a parent of the thing on the right. And in this case, we're violating that because the thing on the right is not a child of the thing on the left. So therefore, no, this is not allowed because mammal is a child of cat, not the other way around. Okay. Next up, we have a couple of calls to different methods. All right, so the first one is m2.breathe. All right, so we have to look up what M2 is. M2 is this mammal. So it's mammal M2 equals new dog. So the question is, am I allowed to call breathe on a dog that's sitting on a class of, or on an object, sorry, that's sitting on a object of type mammal? And the answer is yes, I am allowed to do that. Let's look at why. So again, I'm calling breathe on a dog which is sitting on top of a mammal type. So if we go back to our diagram and we look at this, we can see that our dog has no reference to breathe, but it is a child of mammal which does have a breathe, and that would inherently have come down to the dog. The dog, when it was created, it inherited from mammal, so it got a method called breathe. It didn't redeclare breathe. There is no breathe in the dog. So if I go back and I look at my code for dog, there is no method breathe here. I have a talk and I have a do dog stuff. So it's a bit confusing that I'm allowed to, with a dog, call breathe, because it doesn't seem like it would work, but it does work because the dog inherited breathe from mammal. And I know that it inherited from mammal because of the fact that this is a mammal, but even if this was a dog, I would still be able to say breathe because it's a child of mammal. So the fact that right here it says extends mammal, that's why I'm able to do breathe. If I take out this extends mammal, this statement no longer works, even though I'm sitting on top of a mammal. So just to prove a point here, I'm going to run this code. What are we going to get when we say breathe? Well, we end up with the words generic breathing. So let's see where that came from. The dog doesn't have a breathe method, so nothing in here says generic breathing, but the mammal does have a breathe method. And that just proves that you inherited that from your parent at the moment that the dog extended mammal. That's when I got generic breathing as my definition. If I don't want the dog to breathe with generic breathing, then I need to overwrite it in here and have an override that tells it how the dog actually breathes. All right, next up, M3.breathe. Okay, so this is much like what we just did, except M3 is a cat, it's not a dog. So the first question is this allowed? Are cats allowed to breathe? Again, a weird question, but yes, cats are allowed to breathe because, again, the same thing as before, they're inheriting a breathe from the parent. The difference here is that the cat then decided to override the breathe, and so if we run this code, I still get my generic breathing from the dog, but then underneath it, I'm going to get the output from the kitten, which is to say I have kitten breath. Okay, so let's take a look at why that's the case. Well, I have a public void breathe that's an override here in my cat. I'm changing the behavior of breathing in cats so that I have kitten breath. Notice that has no effect on the dog. The dog just inherited the original version from the parent, and it has generic breathing. But the cat overrode it, and so it has its own version. So the cat is sitting on a class mammal variable type, but it's actually a cat, so I get generic, or I have kitten breath from the cat. All right, and that brings us to our last one. The last one seems pretty obvious, but we're going to have a problem with it. It's m2.talk. Okay, so m2.talk says I'm trying to, on my dog that's sitting on a mammal, I'm trying to call talk. And you might go back to the dog class and you will see that you have a talk method. There it is. It should say I'm a dog. So it seems logical that right here I should be able to call talk on a dog because dogs know how to talk. I told dogs how they talk, that's done right here, and then I made a dog and I'm asking the dog to talk. And it doesn't work. You can see this is highlighted in red and it's not happy with it. It says cannot resolve method talk in mammal. And you might say, wait, why is it looking in mammal? This is a dog, it's not a mammal. Well, this is an important detail that's going to cause you confusion. So hopefully everything that we've done up to this moment made pretty good sense. This next thing that I'm going to talk about is going to throw you for a little bit of a loop, because It's important that you understand it because you're going to run into this problem, but it's a bit non-intuitive. There are two parts to running your code. When I hit that run button in the top of IntelliJ, two completely distinct things happen. The first thing that happens is the compiler syntax checks all of my code to make sure I didn't put any typos in there. And then it converts my code into object code, which means it rewrites everything that I wrote in Java into a new language, which is the Java virtual machine language. That bytecode that it produces is then executed. And so there are two separate moments when errors can occur in your coding. The first errors are the ones that you're used to, because they are the ones that you have all day long. And those are going to be syntax errors. And so when I do something like I say, mammal M1 equals new dog, and then I forget to put the semicolon and I hit run, a syntax error is declared because it'll tell me that right here I'm missing a semicolon. And that's reasonable. That's done by the compiler. It's done before any code is executed. And as a matter of fact, in Java, unlike in Python, it will not begin executing the code until the compiler has actually successfully syntax checked everything and validated that everything is good. This is one of the key differentiations between Java and Python. Python is interpreted. It only reads each line of code when it's about to execute it. And so if there's a syntax error on the 15th line of code, it will have executed the first 14 lines of code before it even notices that there's a syntax error. That's how Python does things. Java does not do that. Java reads all of the code up front, and it refuses to execute if there's a single error anywhere in the code. And this is an important detail that you need to understand, because this is part of the reason why Java is used. I don't want the code to have some weird error that occurs only if you get into a certain branch of the code. In Python, it's perfectly possible to write code that has an if statement with an error in the if statement that most people will never get to. But once every now and again, somebody will hit that if statement, and then they'll see the error and the code will crash. And that's a really, really bad experience from the user. That's like if you open an app on your phone and it works perfectly until you hit a certain button. And as soon as you hit that button, it crashes every time. That's because you've hit a block of code that has an error in it. And that's not good. So to prevent that, Java checks everything. Whether you're actually going to execute it or not is irrelevant. If you put the code in the file, Java's going to check it and make sure that it's syntactically correct as part of the compilation before it even begins executing. All right. The second reason why Java has to do that is because in Python, it actually interprets each line one at a time. When you do something like, x equals 7 in Python, it says, okay, do I have a variable x? Yes, I do. Here it is. Okay, its new value is 7. Life is good. But it's doing that right then when it read that line of code. It doesn't understand beforehand what 7 is or what x is. It has no idea. Whereas in Java, while it's doing the compile, it actually checks all of this. It looks at it and it says, x, do I know what x is? Yes. Is it an integer? Because I'm about to try and put an integer on it. Yes, it's an integer. Okay, then this is going to work. I'm happy with this line. Okay, I forgot my semicolon. But I'm happy with this line. I'm going to move on. What Java then does is it actually converts this into bytecode. So I've said that a moment ago. Let me explain what that actually means. The main selling point of Java, which seems weird because Python kind of feels like it's the same way, but the main selling point of Java when it came out originally was that it can be run everywhere. And what that means is, up until Java came around, most languages were compiled down to a specific set of hardware. So, for example, if I was writing code in C, and I'm sitting at a Dell computer here that's running with an Intel processor, when I wrote my code, what the compiler did for me in C was it compiled it down to the instruction set that that Intel processor on that machine understands. And if you take that C code and you try to run it on a Mac, which is not running an Intel processor, it's probably running something else, then it won't work. Because the instructions that the actual processor, the CPU, understands are different from each machine. The instructions that your phone understands and the instructions that your desktop PC or your laptop Mac understands are all different from each other. So the same piece of code used not work on different machines. If you wanted your block of code to run on a Mac, you had to separately take that code, go to a Mac, compile it on the Mac, and then it produced a binary that worked on a Mac, which only works on a Mac, and it's separate than the binary that works on Windows that only works on Windows. And you've probably seen this. If you've gone to download a piece of software, sometimes you have to get a very specific piece. You have to get the the Windows download versus the Mac download. If you've gotten a game, sometimes it only runs on one console. It may only run on a PlayStation. It may only run on an Xbox. It may run on a PC, or maybe you have to get different versions for each of them. So the selling point of Java originally was that it runs anywhere. And the way that they were able to make that work is instead of your compiler compiling it down to the actual language that that particular CPU understands, it instead compiles it down to a middleware, something that it then interprets separately. So what they did was they wrote what's called a Java virtual machine that runs on Intel. And then they wrote a separate Java virtual machine that runs on a Mac. And then they wrote a separate Java virtual machine that runs on a phone. They wrote a separate one that runs on an iPhone. And they ran a separate one that runs on a projector. And they wrote a separate one that runs on every type of hardware that exists in the world. They wrote that virtual machine such that it takes the instructions that are produced by the compiler when it compiles your code, and then those instructions are run on the virtual machine, which knows how to deal with the hardware that it's sitting on. Now, all of a sudden, I can write the same block of code, and I can run it on a Mac, on a Windows machine, on an iPhone, on an Android phone, or even on a projector. That was the selling point of Java. The downside of this idea is that because your code has to be compiled down to this bytecode, this Java bytecode, and then that bytecode has to be actually executed on a virtual machine, it runs slower than code that's natively compiled for the particular processor you're on. So this is why you'll hear people say Java is slower than C++. It is. Any code that you write in C++ that's compiled specifically for that one machine will execute faster than code written in Java. And Python is slower still, because Python doesn't even go down to a virtual machine that runs there. Python has to interpret it as it's going. Every single time you run your Python code, it has to reread it and re-understand the entire thing from scratch, which is not true in Java. It's already syntax checked it before you ever start running it. So this is a trade-off that people can choose what makes sense. If raw performance is the most important thing to you, then you're probably going to want to compile it down directly to the native hardware that you're going to run on. But the side effect of that is you're going to have separate versions of it for every machine. And if you take something like the Unreal Engine, it's all written in C++. And that allows you to build games that are really, really fast. And so Unreal is going to be the fastest of the engines. But it only runs on machines that Unreal runs on, that it's already compiled for. And so you have a limited audience that you can market your game to. Whereas if you take something like the Unity engine, it's written in C#, which is pretty much a derivative of Java. And so in that case, it has the same idea where there's a virtual machine that's effectively running the code. And so because of that middleware, you get more flexibility. You can run it on a phone, you can run it on a Mac, you can run it on Windows. But the downside is, well, you don't get all of the speed that you had before. Okay, so this was a long aside to explain what Java bytecode is. And the reason that I bring this up is because as the compiler is trying to interpret your code and actually write the bytecode for you, it has to know whether each thing is correct. And so our example of int x equals 7 in Java, it validates that 7 is an integer, it validates that x is an integer, and it says, yes, you're allowed to assign an integer to an integer. So let's come back to the code that we were looking at a few moments ago, the code that's been on our screen this whole time. So what I asked it to do was I asked it to call the method tog on an M2. So what the compiler is going to do is the compiler is going to look at M2 and it's going to figure out what type M2 is. And the answer is M2 is a mammal. Now, I know I put a dog on there, but the type of the variable is a mammal, and that's the important distinction that you must understand. The type of the variable is mammal. So the compiler looks up the type of the variable. So the question is, does mammal have the ability to talk? We go to mammal, and we see there is no talk method. So no, the compiler is not happy with this line. Now, what's weird is that in reality, the variable is of type mammal, but what's actually sitting on the variable right now is a dog. And I know that, and you know that, but the compiler doesn't know that. And you might say, but it does. It can look at that line 3 lines above it, and it can see M2 equals new dog. It's right there on the screen. So why is it not able to see that it's a dog? Well, because it may not be able to see that it's a dog. We said a long time ago that this is called late binding. It doesn't know that that's going to be a dog always. Now, in this exact piece of code that I've written, it can only be a dog. There is no differentiation, or there's no circumstance under which M2 is not a dog. So you and I are both correct that if it was smart, it would be able to see that that really is a dog right now. But it's not going to accept that. And the reason it's not going to accept that is because I could add in some code here that would make it so that the compiler has no way of knowing whether that's actually going to be a dog. So I can make a random object. All right, I'm going to go ahead and import random because it's not here. There we go. All right, then I'm going to make a random number. So int x equals rand.nextInt, and I'm going to pick a number between 1 and 3. Or 0 and 3, it's 0, 1, or 2 is what that's actually going to be. All right, now, the line of code that was in question was mammal M2 equals new dog. Using my new random object that I just created, I'm going to say if is equal to 0, then mammal, let's create mammal above here, M2. So that just declares M2 as a mammal. Now I'm going to say M2 equals new dog. If x is equal to 1, M2 is equal to a new cat. Okay, I'm going to get rid of this line. This was the original line of code that was here. I'm just going to comment it out. Figure out how to type again. And now I'm going to ask you, can the compiler be 100% sure what M2 is going to be? And the answer is no, it cannot. The compiler no longer gets to decide what M2 is, because the compiler never gets to see that random number being generated. That's what's going to happen in runtime when the bytecode is being run. So right now, the compiler is having to decide whether you're allowed to say talk on an M2, which is a mammal, and the answer is, I don't know. As a compiler, I cannot be 100% sure that that is going to come out as a dog. As a matter of fact, given the current code with this if statement and this random number generator, I literally have no idea. It could be a dog, it could be a cat, getting all caught up here. And so the dog and the cat could be generated in runtime. This is what's called late binding. And so as a result, the compiler is not happy with that m2.talk. If I want the compiler to accept that m2.talk, I have to very specifically put a dog on there and then use something called a cast to tell the compiler, this really is a dog right now. All right, so let's talk about casting. You've seen it before in the past, but you've usually used it for numbers. So if you have something like double x equals 7.34, and you need to pretend like it's an integer for a moment, you might say int y is equal to, and then you can cast it to an int by putting parentheses on front of it. That's going to take the x, and it's going to pretend like it's an integer. So 7.34, pretending like you're an integer, is just going to be 7, and so the value of y is now going to be 7. This is called a cast, and you've done this in a couple of circumstances in the past. Usually it's with numbers, but you can actually cast more than just numbers. You can cast objects from one type to another, as long as they are parent-child relationships. So you can cast a dog to a mammal to a dog, that kind of thing. So that's what we're going to have to do here. We're going to have to use a cast on this in order to make this M2 talk work. And the way that we're going to do that is with this line of code. We're going to put the word dog in parentheses on front of M2 and then call talk. So your first guess would be to do this. And that is almost right, but it has a precedent problem. So you actually have to do this, which is you have to put another set of parentheses around the first part. Now you can see that it's happy with that line of code. So to be clear, this is the cast. I'm casting it to a dog, but the extra set of parentheses are because the default behavior without these extra parentheses, so if I take these back out again, is it's going to call talk on M2 and then cast the result to a dog. That's the order of precedent with regard to casting and method calls. The method call happens before the cast. So to force the order of precedence such that it does the cast on the M2 first and then calls talk, I have to put another set of parentheses around it. So that allows me to now make M2 into a dog and call talk on it. Now I have a problem, which is I may have inadvertently made a cat. I was here creating animals and somehow I was doing it with random numbers, and maybe I made a dog, maybe I made a cat, I have no idea. On this line, it's allowing me to cast it to a dog, but what happens if it's actually not a dog and it's really a cat right now? Then I have a problem. So I want to check, is M2 an instance of dog? If it is, then call talk. If it's a cat, I'm actually not going to do anything because cats don't talk. Or do they talk? Do cats talk? No, they don't, because they didn't implement talkable. So the cat cannot talk. So I definitely don't want to make that line say cat m2.talk, because that's not allowed. As a matter of fact, if I try to cast it to a cat, it won't allow me to do that, said he confidently. Yeah, it says, no, you can't do that. Cannot resolve method talk in cat, because cats don't talk. Duh. So ultimately, this is not allowed. It only works for the dog, and it works for the dog because the dog is an instant or implements talkable, and talkable has the ability to talk. That's how it's able to check that. So to review all of that, I realize I went off on a tangent about compilers, but it's an important distinction. The way that that line of code is going to be executed is we're first going to talk about the compiler. The compiler looks at M2 and says, that's a mammal. And it goes to check talk if it's not cast. But since it's now cast to a dog, the compiler says, okay, M2 is a dog, and that's plausible because dog is a child of mammal. So I'm going to let you cast it to a dog. And now, based on the fact that it's a dog, I'm going to allow you to call talk because dogs know how to talk. That's the level of detail that the compiler is checking for. And I know it's really, really picky and it's really confusing here because it seems like it should just work. Dogs know how to talk. I wrote a talk method in a dog, so why doesn't it know how to work? Why am I having to do all this? It's simply because you're using polymorphism, which is late binding, and the compiler can't be sure when you're dealing with that. If you're doing early binding, you're not using polymorphism. It's just a straight dog d equals new dog. You've no problem. You can call d.talk all day long and everything will work fine. This only happens with polymorphism where you've got an object that is currently cast to some other type, or it's a child of some other type, and therefore it's ambiguous to the compiler because the binding is not going to happen until runtime. That's when you're going to need to do this cast. Okay, so that was a really long explanation for m2.talk. It is possible to do it, but you're going to have to do it with a cast in order to make it work. So this just talks about what I said about the parentheses needing to be around the outer side. Okay. So let's put all of this together. Let's make an array list of mammals, which we're going to call animals. This is out in my main, and so we're going to say array list mammal equals new array list of mammals. All right, and so that already went ahead and added it in. So now I can add into my animals new cats and new dogs. Okay, so let's talk about this. How am I able to do that? And let's do the same thing for dog. Well, animals is of type mammal. Okay, in reality, it's a type array list of mammal, but each cell is of type mammal. So animals is able to hold mammals. Cats are children of mammals, so therefore I'm allowed to put a cat in there. Dogs are children of mammals, so therefore I'm allowed to put a dog in there. So the array list is of the parents type, and the children that I'm putting into it are actually of the child types of cats and dogs. So that allows me to put a cat in there or a dog in there. Now I can use a for each loop. So I'm going to say for mammal m in animals, what I'm going to do is I'm going to ask it to do m.read. So is that possible? Well, I have to spell it correctly in order for it to work. That is definitely going to work no matter what. So let's talk about this. It's going to go through all the animals that are in my array list. And there could be hundreds of them, right? There's no rule that there has to be 2. Right now there's 2, but obviously I could produce hundreds. And it's going to ask each of them to breed. Is that allowed? Well, the answer is yes. I can be sure that no matter what animal is in each cell, that animal will know how to breed. And the reason that I can be sure of that is because the type of the array list is mammal, and all mammals know how to breed. It's defined in mammal. That's the beauty of this polymorphism. That's the beauty of having these child-parent relationships where they are able to talk to each other in a way where the inheritance is causing stuff to come down. I don't have to worry, does a dog know how to breed? Does a cat know how to breed? The fact that they are mammals means that they know how to breed. It's just inherent. So yes, I can do that. Then, if I have a dog, so if M is an instance of dog, what I'm going to do is I'm going to ask the dog to talk, or actually I'm going to ask the dog to do dog stuff. And if it's an instance of talkable, not cat, talkable, then I'm going to ask it to talk. Now that last one is interesting. Again, I'm going to have to cast it to talkable. But basically what I'm saying is, going through all of the animals, if the animal can talk, have it talk. So we have this array list of dogs and cats. I don't actually know how many dogs and how many cats I have because I could certainly be generating them with a random number generator. Just like I generated the random number generator a minute ago, I could do that in the loop and fill up the array list. And so I have some number of dogs and some number of cats. And then what I'm doing is I'm walking through the array list and I'm saying, you talk, you talk, you talk, you talk. And I'm guaranteed that if they are a talkable character, they will know how to talk. So that's what my instance of talkable is doing. If they are an instance of talkable, they're able to talk. So the dogs will answer, whereas the cats will get ignored because they don't know how to talk. I don't have to deal with a whole bunch of if statements that says if it's a dog or a parakeet or a giraffe, then call this method. If it's a elephant or a, whatever. I don't have to write all of that code. I simply say, if it knows how to talk, ask it to talk. That's literally what that code says. If it's an instance of talkable, then ask it to talk. And if I have other interfaces in there, like walking ones, I can say if it's an instance of walkable, then tell it to walk. And then all of my characters will start moving around in the game without me having to write very specific code for each and every one of them. All right, so all of the objects in the list were mammals. They're not cats or dogs, even though I'm putting cats and dogs in there. When you pull something out, it's a mammal. So I'm able to use instance of to say, well, is this particular mammal really a cat or is it really a dog? That's what instance of does. It's a really cool little feature that you have there. And then I'm able to call methods on them after casting. Okay, so that brings us to the end of module number 3. Again, a huge module with a whole lot of information in here. I know for most of you, this is going to take a little bit of time to sink in because there was so much different stuff in here. And even though all the rules are fairly easy for each individual thing, keeping track of all of it at once is going to take a moment. So you definitely need to practice this and keep doing examples of this to understand what is allowed and what's not allowed. The types of questions we're going to ask you in lecture is we're going to give you some code with some interfaces in abstract classes and concrete classes and ask you, can you instantiate this? Can you call this method on this? What would be the output if you call this method on this? Those types of questions, very much like what I did in today's lecture. So that's why we have this lecture here. It's a good summary of everything that we did. And if you understood everything that I just talked about today, then you're probably in decent shape. You just need to make sure that it's concrete in your head. But the ideas are all covered in this slide set that we just did here today. So that's the end of module number 3. The next module, we're going to talk about recursion, and I will see you guys in there soon.